Hi guys, Jonathan Lambert here with the Mathematics Development and Support Service at National College of Ireland. I think this is probably my third live. This is my third or my second live stream now at this stage? Oh, this is my second live stream with you guys. I'm just going to say hi, hi everyone, hi everyone. First of all, hi everyone, and can you hear me okay? Can you hear me okay? I think there's two people there that are currently let's say have joined the live stream. So I'll just maybe just post that there just to see who I have with me. Uh, Hi everyone, can you hear me okay? I'll just probably just give it a second here before. I'm just waiting for maybe a reply to. Okay. There's Celine. Hi, Celine. Brilliant, Celine. And I did get your question there earlier. I've actually printed off that exam paper. So I printed off that past exam paper, and I will run through that particular question that you asked me to go through, which happens to be an independent samples t-test. So I will do that. Okay. So hopefully you've heard me. You heard that grand. Oh yes, you can hear perfect. Brilliant. Okay. And I think there is somebody else there, but maybe that's someone from the class. I have Celine. I was asked another question as well just before your question came in, which was, can I sort of give an overview of all the tests? That's a big word to use there. All the tests, all the hypothesis tests, and when to use them. So maybe what I'll just do first of all is I'll try to give an overview of the different types of tests and when to use them. First, let's maybe just clear up some symbols. Yeah, so some important symbols. Okay, so important uh, symbols that we're going to use. Okay, we have two perspectives. We have the population parameters, okay, population parameters, and we have the sample statistics, okay, the sample statistics. Um, and let's say when we consider the population, we could consider the mean value, okay, of a population that's symbolized by mu. In the sample case, that's symbolized by x bar, okay. Then we have the variance, let's just say the var, that's symbolized by sigma squared. And in the sample case, it's symbolized by s squared. Then we have the standard deviation, let's just say st dev, okay, that's symbolized by sigma in the population case. So if you're calculating the variance or the standard, if you're calculating the standard deviation of all your population values, it's sigma. In the sample case, it's s. And some other important things, symbols, would be, let me just think here for a moment. Let's say correlations. Okay, so if you're going to calculate a correlation, well, if you have all the population data, the correlation symbol is rho. Otherwise, it's or, and maybe also maybe in relation to regression. Okay, so in a regression and a regression line, you have, let's say, we have parameters which are, let's say, the intercepts and the slopes. They're typically betas, okay, whereas in the sample case they're b values, okay. What I really want to try to get across is this is because when we define a hypothesis, when we define a hypothesis, uh, we know that there's two parts of it. There's the null position and there's the alternative position, okay. But the important thing is that the hypothesis is always a statement. It's always a statement about about a population, about population parameter. Okay, population parameter. That's really important. Okay, that the hypothesis itself is statements about population parameter. So these hypotheses, the only things that can appear in them hypotheses are effectively these symbols down here. Okay, and there's many more of them as well. Yeah, but let's say the common ones that we might be interested in is some tests in relation to the average or the mean of a population, some tests in relation to its variance or standard deviation, some tests in relation to correlation value, and some tests maybe in relation to regression coefficients. Right? And there are many more I mean, you could have a look at skewness, you could have a look at kurtosis, the population skewness, population kurtosis, and you could assess its value to see whether it's a specific value or not through a hypothesis test. Right? So, with that in mind, our hypothesis then, well, we can test any one of these things down here, if that makes sense. Yeah. Okay. So what I'd like to do is I just maybe want to go through the types of tests that we could have. Okay. So where I like to start is this: is to ask a question first. So I'm going to just build a tree. Okay. And is to ask a question, and the question is, how many groups do we have? Okay, if that makes sense. Yeah. So how many groups of data do you have? Do you have just a single group, one group? Do you have two groups, or do you have more than two groups? Okay, so more than two. Okay, so that's a nice. I think that's a nice place to start in relation to trying to figure out what tests to do. Okay. Okay. If it's a single group, well, then it's called a single sample test. Okay, that's called a single sample test. Okay. Uh, and this a single sample test can be a test of any one of these particular parameters down here. I mean, we could test the mean by a single sample test. We really mean we're testing whether the population we're testing, okay, testing if the population parameter, okay, uh, takes on a specific value. Okay, takes on a specific value. Okay, so that's what we're talking about. Maybe I'll just gonna make this a little bit bigger here, okay? Just so that I have a bit more room, okay? So let's just go back to this here again. So let's just keep our parameters over here because there's so many different tests that we can undertake. Okay, so the first question is the number of groups that we have. Okay, so how many groups have we got? Okay, do we have one group? Do we have two groups? Or do we have more than two? Okay, more than two. Okay. In the case where we have one group, and just keep in mind, as I said, is that we can test to see whether the mean takes on a value, or whether the variance takes on a value, or whether the correlation is a value, or whether the regression is a value. Okay. Uh, we probably need to ask ourselves. So we know the groups. Okay. We probably need to ask ourselves the size of the groups. Okay, if that makes sense. So let's say the group size. Okay. Uh, how large? How large? Okay. Are the groups? Okay. That's an important thing for us. Okay. And large is a question that I suppose it's not an easy question to answer. Yeah. Okay. And you have to do what's known as a power analysis to try to identify a specific value in relation to how large the group is, how big is our sample. But typically we might have is it bigger than 30? Are there 30 or more observations in the group? Okay. If there are 30 or more observations in the group, okay, right, and it's a typical place where we would be if there are 30 or more observations in the group. And also if the variance is known. Okay, the variance is known. Okay, in other words, we know the value of sigma squared. Okay, the variance is known. Well, then where we are is we're into a single sample Z test. Okay, right? So we do a single sample Z test when we want to test a specific value. Okay, in this case, let's say a population mean value against a specific value. But we do it when we have one single group, the number of observations is greater than 30, and the variance is known. We do a single sample t-test. Okay. Now, in the situation where we've got less than 30 observations, okay, and SPSS actually always does t-tests and anyway, okay, in the situation where we have less than 30 observations, okay, where we're actually going to go to is we're going to go to a single sample t-test. Okay, that's what we're going to undertake when we have less than 30 observations. Okay. uh, if we have the situation where the variance is unknown, okay, if the variance is unknown but the sample is greater than 30, okay, we can also rely upon the central limiter, and we can also go with a single sample Z test. But let's just demarcate it that our journey is taking us to one of these particular outputs here. Okay, so you're either got a single sample Z test or a single sample T test now in this case, depending on whether the samples are big or whether they're small, whether the variance is known or not known. Okay, now when we look at the two groups situation, okay, so like the one group situation might be testing whether the average wage, okay, the average industrial wage is less than or greater than or different to a specific value. Okay? The two group situation is where we're comparing two groups against each other. So it might be males compared to females. It might be a pre-test and a post-test. Okay, but the thing about the two group scenario is we have to sort of ask ourselves. We have to ask ourselves. I suppose, are the two groups independent of each other or not? Okay, so if the two groups are independent of each other, okay, we're going to come down this particular avenue here. Okay, and then we're into the situation of whether the group size. And don't forget, we've got two groups here. Yeah, so we've got N1 sample sizes, and we've got N2, and if they're bigger than 40, okay, and also if the variances are known, okay, if the var are known, well then what we're into is we're into a z-test, yeah, okay, a z-test for the difference between two population mean values, okay. So we're still into a z-test here in that case, yeah. If the sample sizes are less than 40, okay, well we're into a t-test. We're into a t-test in that situation, if that makes sense. Okay? Similarly, now if they're dependent on each other, okay, so the independent situation is let's say is where we have two samples, males and females, they're not interacting with each other in any way. The dependent samples case is where we would have, let's say, a pre and a post measure on the same individuals, as an example, right? The dependent samples case, once again, well, the dependent samples case, we're actually going to go just, let's say, for a t-test in that case. Okay, if that makes sense. Okay, where we have more than two groups. Okay, when we have more than two groups, we're into what's known as an analysis of variance and ANOVA. Yeah, okay? And I don't know whether they have covered ANOVAs with you at this stage. These are all parametric tests. Okay, and actually, also all of these tests are all got to do with the population mean and testing population mean values. Okay, but when we have more than two groups, we're into an ANOVA. So really, I suppose when we have one or two groups, we're into z-tests or t-tests. If the sample size is relatively big, we're into a z-test. If the sample size is relatively small, we're into a t-test. Okay. If the population variance is known, it's a z-test. Okay. If it's unknown, we're going to estimate it by s squared, which is the sample variance. Okay. In which case, we're into a t-test as well. Okay. Let's just keep that in mind. And then maybe just one final thing just to maybe look at is when we look at all them population parameters in the hypothesis. So let's say that we might have what I haven't talked about here is I haven't talked about the situation where we want to test variances and things like that. So let me just maybe run through that, the distributions themselves. Yeah, okay? What distributions go with what, if that makes sense. Okay, so the appropriate distributions. Okay, distributions. Right? Well, if we're testing a mean value, a population mean, right? The distribution is either the z distribution, right? The z distribution or the t distribution, right? T distribution. In other words, it's normal, right? In some in the sense of normality. Okay. If we want to test a population, let's say variance, okay, so testing a population variance against a specific value, okay. This is like a single sample test, okay. Well, then the distribution is a chi-square distribution. Okay, so we want to test sigma squared, let's say, is equal to 30. Let's say that's the null position, and the alternative is that sigma squared is not equal to 30. That's a two-tailed test there. Okay, the appropriate distribution to use is a chi-squared distribution. Okay, if we want to test, let's say, the difference between two population variances, the difference between two population variances, okay? Well, the test distribution. So in other words, we have, let's say, H0. We want to test whether sigma, let's say sigma squared for group A is the same as sigma squared for group B. That's our null position. We're going to assume that to be true. And let's say sigma squared for group A is different to sigma squared for group B. These are variances, population variances. This is the hypothesis here itself, all wrapped up into a null and an alternative. Okay? So if we want to test for the differences between variances, okay, well then what we have is we have an F distribution. Okay, so that's an F distribution. Okay? Is the distribution to use in that particular case. Yeah. Let's say if it's a correlation coefficient, so we're testing a correlation coefficient. Okay. So let's say a rho. So H0 might be that the correlation is equal to 0, or HA that the correlation is not equal to 0. Okay, that's the hypothesis. Okay. Well, when we test a correlation coefficient, don't forget we've calculated a sample correlation, which is R. Okay. Well, our test statistic. The test statistic is actually a T statistic. So this is actually a T distribution. Actually models a correlation coefficient. And similarly, if you want to test a regression value, right? So when it comes to the regressions themselves, and you have a regression model. So let's say we're testing a regression parameter. It could be the intercept, or it could be a slope, H0, where we're saying that beta is 0, the intercept is equal to 0, or HA, the beta of 0 is not equal to 0. So we're saying that either has an intercept at 0, or it doesn't have an intercept at 0. That's the test. Well, in which case we're also into a T distribution for that particular test as well. Okay? And then maybe finally is the ANOVA, the analysis of variance. Okay, I can't see any tests other than these tests in relation to these distributions. The analysis of variance, which is the ANOVA, we're into an F distribution. We're into an F distribution for that particular test as well. Okay, which is the mean sum of squares between relative to the mean sum of squares within. Okay, but anyway. So let me just maybe run through this again, because actually the question that was asked was what distributions do you use for what tests? Okay, well, when we're testing population mean values, okay, mu's, it's either a Z distribution or T distribution. So they're the tables you go to. When you're testing a population variance, okay, that's sigma squared. Okay, well, if it's a single sample test, we're going to a chi-square distribution. Okay, if you're testing two variances against each other, okay, well then we're into an F distribution. Okay, the test statistic actually is F is equal to S1 squared over S2 squared. It's the ratio of the two variances. And if you're testing a correlation coefficient, the test distribution is the T distribution as well. Okay? So that was asked earlier on by a student, was in relation to maybe if I could run through just what distributions I used and what cases. Okay, so what I want to do now is maybe just to move on and to answer the next question that was asked. And Celine, you actually asked a question, which was to undertake or to run through an independent samples Ttest. Okay, which is the test that's in this National College of Ireland exam paper, semester 2, 2019. Thursday, the 9th of May 2019, if I'm not mistaken. And the question that you asked me to run through is this question here, question 1, which is in relation to a study is being conducted to establish if there is a difference in time taken by left-handed and right-handed golfers to complete a round of golf. Okay, so let me just maybe clear this table off here. Okay, I'll clear the paper off here, and let's get started on this particular question. Okay, so maybe just to run through this scenario. So this is going to take probably take about half an hour to get through, because there's a fair bit involved in it. Yeah. Okay. But maybe just let's set the scene here. Yeah. So a study is being conducted to establish if there is a difference in time taken by left-handed and right-handed golfers completing a round of golf. Okay? So we want to know who's going around. There's left-handers and right-handers going around taking part in a game of golf, and we want to know who gets around the course quickest, basically. Yeah. Okay. Or is there a difference in the time that takes? Yeah. Effectively, the time in minutes taken by each golfer to complete an 18-hole round was recorded and is presented in the table below. Now let's just actually just do this from a sample size perspective first of all. So I've got the first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rows. But in relation to the first group, okay, in relation to the first group, there is the sample size is 11. So N1 is equal to 11. Okay? And now I know that's very small. I'm going to write this out again now in a second. Yeah. In relation to the second group, we have the sample size N2 is equal to 12. So no matter what, if I actually go back and if I have a look at what I mentioned earlier on in relation to trying to decide your tests, okay, so let me just get that sheet here. I don't know whether this does this any justice here. Okay? We have two groups. Okay? We've got the left-handers and we have the right-handers. Okay? And they're independent of each other. Okay? They are independent of each other. But we don't have both group sizes greater than 30. That's important. Both group sizes are less than 30. Okay? So because the group sizes are less than 30, we're actually going to be into a t-test situation here. Okay? So because we have small sample sizes, we're going to rely upon a t-test. Okay? If that makes sense. So now what we have is an independent samples t-test. Okay? So I now know that the appropriate test is an independent samples t-test. Okay, t-test. Now, but let's just keep in mind that there's two variants. There's two variants of this test. Okay, there's two variants of the test. There's the one that assumes. Okay, there's one that assumes that the two groups themselves have been randomly selected from populations that have the same variance. So that assumes equal population variances. It doesn't mean that we know them. It just assumes that they're equal. And then the second variant of the test, okay, because this, depending on which variant we go with, okay, determines the test statistic. The second variant assumes that they're equal population variances. Okay, so effectively, before we can actually do the independent samples t-test, we need to figure out whether the variances are equal or unequal. Now, if I go back once again, where's that concept? Okay. Oh. If I go back here to what we said about if we want to test for variances, if I want to test for the difference between two population variances, I need to do a hypothesis test and the distribution, associated with that is an F distribution. So actually, effectively, what we need to do is we need to test to see whether our variances are equal or not equal, if that makes sense. So the steps I'm going to follow now is this, yeah. So my stage, let's say stage 1, okay, is to do a hypothesis test, okay, of two population variances. Okay? So the hypothesis is going to be, let's say, something like H0, yeah, that the variance of the left-handers is the same as the variance of the right-handers, okay? And the alternative is going to be that the variance of the left-handers is different to the variance of the right-handers. We're going to assume this to be true. Assume true. We're going to assume the null to be true. And we're either going to reject or we're going to fail to reject. Okay. If we fail to reject, we continue to the next stage. Yeah. Okay. To stage, let's say stage 2. Okay. Which is an independent samples t-test. Okay. Assuming equal variances. Okay. If we reject on this test, well, then we'll go to, let's just call it stage 3, okay, which is we'll do an independent samples t-test, okay, assuming unequal variances, because we've rejected away from the null, and the null is assuming them to be equal, okay. So we'll do an independent samples t-test assuming unequal variances. Okay? So effectively, before we can actually even do the independent samples test, we have to do a test of the variances. So let's do that. So what we need to do is we need to calculate the variances of both of those groups. So what I'm going to do now is I'm just going to write down all of those values. So this is going to take a little bit of time, guys. Yeah. So I've got the left-handers and I've got the right-handers. Okay. And what we're going to do is we're going to just, I'm going to write these down. I'm going to just go through this. So that's 146.0, 152.0, 152.4, 157.4, 165.1, 150.2, 146.2, 160.3, 152.0, 155.8, 145.9. That's the first group, left-handers. The right-handers we have, it's 144.8, 153.9, 148.1, 144.8, 147.9, 140.2, 138.4, 144.2, 152.0, 155.8, 148.1, 144.8. So there's my two groups. Okay. I suppose the first thing we probably really should do is, because we're going to calculate the variances of them, we need to calculate the mean values of both of those groups. Okay, so let's do that. So just recall the formula. So our mean values are x bar is the sum of all the observations divided by the sample size. So I'm going to calculate an x bar for the left-handers, and I'm going to calculate an x bar for the right-handers. Okay, so I need to sum up all of these values here. So let's do this on the calculator. So we have 146 plus 152 plus 152.4 plus 157.4 plus 165.1 plus 150.2 plus 146.2 plus 160.3 plus 152.0 plus 155.8 plus 145.9 gives us a total summation of 1683.3. So 1683.3. That's going to be my sigma x. Okay, and there are 11 observations, so the mean is going to be 1683.3 divided by 11, which gives us a value. I'm going to divide that by 11, which gives me a value of approximately, I'm just rounding that to 153, okay, to the whole number. Then I'm going to sum up the right-handers. I want to calculate their sample mean. So it's 144.8 plus 153.9 plus 148.1 plus 144.8 plus 147.9 plus 140.2 plus 138.4 plus 144.2 plus 152.0 plus 155.8 plus 148.1 plus 144.8 gives us a summation of 1763. And hopefully I haven't made any mistakes here. This is probably a bad example to use, Celine, when I'm live here, because there's so many numbers here, and it's going to take us a while to get through it. But anyway, we now have the mean of the right-handers. It's the sum of the observations, which is 1763 divided by the sample size. There's 12 of them, so divide that by 12. So when I divide it by 12, that gives us, that's 146.9, which is approximately equal to 147. Okay. So there we go. Now we have the two mean values, which is good because we're going to need these later on when it comes to the independent samples t-test. Okay? So there's our two mean values, our two sample means for these two samples that have been randomly selected from some population, okay? Population of golfers. Yeah? Yeah. Now what we need to calculate is we need to calculate the variances, and keep in mind that the variance formula, S squared, it's the sum of squares, so it's the distance that each observation is away from its mean value squared divided by the sample size minus 1. So we need to calculate this for each one of those groups. Okay. So what I'm going to do is I'm just going to just concentrate on the right group. Okay. So I'm going to calculate x minus x bar for the right guys squared. Okay. And then what we're going to do is we're going to do x minus x bar for the left. I should have done the left guys first. Let's say for the left guys, and then for the right guys squared. Okay. So when I sum up this here, this column here, this will be the sum of squares for the left-handers, and this will be the sum of squares for the right-handers. So for the left-handers, what we need to do is we need to take the mean value away from each one of these values, and then we need to square it. Okay. So keep in mind, for the left-handers, the mean is 153. So I need to take away 153 from each one of these values. So you see we have 146 minus 153, which is straightforward enough. And when we square that, we get a value of 49. Okay? So it's 49. Then we have 152 minus 153 gives us 1. 1 squared is 1. Then we have 152.4 minus 153 gives us 0.6. 0.6 squared gives us a value of 0.36. Okay? Then we have 1.574 minus 153, which gives us 4.4. So 4.4 squared gives us a value of 19.36. Then I'll just put them all in. 165.1 minus 153 gives us a value of approximately 12.1. When we square that, we get it's, oops, daisy. So we've got 165.1 minus 153 square it gives us a value. I made a mistake there again. 165.1 minus 153 square that gives us a value of approximately 146.41. Then we have 150.2 minus 153. When we square that, that gives us a value of 7.84. 7.84. Then we have 146.2 minus 153. When we square it, that gives us a value of 46.24. Then we have 160.3 minus 153. When we square it, that gives us a value of 53.29. Then we have 152.0 minus 153 gives us 1. 1 squared is 1. Then we have 155.8 minus 153. When we square it, that gives us a value of 7.84. Then we have 145.9 minus 153. Okay? When we square that, that gives us a value of 50.41. 50.41. Okay? And then when we sum these guys up, so let's just sum these up. So we have 49 plus 1 plus 0.36 plus 19.36 plus 146.41 plus 7.84 plus 46.24 plus 53.29 plus 1 plus 7.84 plus 50.41. That gives us a total of 382.75. So we can calculate now the variance for the left-handers. So it's the sum of those sums of squares. Yeah, it's the sum of those squared distances. So we have s squared for the left-handers is equal to 382.75 divided by, well, there's 11 of the minus 1, so divide by 11 minus 1, which is divided by 10, which gives us 38.275. Okay, and that's our first variance, okay, which we're going to need for this hypothesis test now in a moment. Yeah. To calculate the variance for the right-handers, once again, we need to take the mean away from each one of these. So I'm going to do this. So we have the mean is 147. So we have 144.8 minus 147, and we're going to square that to give us a value of 4.84. Okay. Then we have 153.9 minus 147, and we square that. That gives us a value of 47.61. Then I have 148.1 minus 147. When I square that, that gives us a value of 1.21. Okay. Then I have 144.8 minus 147. When I square that, that gives us a value of 4.84. Then I have 147.9 minus 147. That leaves us with 0.9. When we square it, we get 81 or 0.81. And then we have 140.2 minus 147. When we square it, that gives us a value of 46.24. Then we have 138.4 minus 147. And when we square that, that gives us a value of 73.96. Then we have 144.2 minus 147. When we square that, that gives us a value of 7.84. Then we have 152.0 minus 147. And when we square that, that gives us a value of 25. And then we have 155.8 minus 147. When we square that, that gives us a value of 77.44. Then we have 148.1 minus 147. When we square that, that gives us a value of 1.21. And finally, we have 144.8 minus 147. When we square that, that gives us a value of 4.84. So 4.84. And we need the sum of all of those squared distances. Yeah. So we need 4.84 plus 47.61 plus 1.21 plus 4.84 plus 0.81 plus 46.24 plus 73.96 plus 7.84 plus 25 plus 77.44 plus 1.21 plus 4.84 gives us a total of 295.84. But the important point here now is that we now have the variance for the right-handers. So we have S squared for the right-handers is 295.84 divided by just 12 of them minus 1. So divide that by 11. Oops. So we have 295.84 divided by 11 gives us a value of 26 point, let's say 20. I went to 3 decimals here, so let's go to 3 decimals here. 26.895. Okay, that's the variance. That's the variance for the second group. Okay, Celine, I hope you're still with me. There was a lot of work involved in just getting our appropriate statistics that we require to do the test. So what I'm going to do now is I'm going to move on now, and now we're really ready to do. We want to figure out what independent samples t-test to do here, whether it's the equal variances one or the unequal one. So now I'm ready to move on to do the actual test itself. Okay, so moving ahead, we have. So moving ahead now. So now I'm into the F test. Okay. So here's my, let's say, the test of the difference between two population variances. Okay. So it's just a hypothesis test. It's a 5-step process. Okay. So this test itself. So we have the hypothesis. Well, it has a null position. It has an alternative. The null, we assume that there's no difference. So we assume that the variance of the left-handers is the same as the variance of the right-handers. Okay? And the alternative is, no, we don't have to do that. We just want to find out whether they're different, whether the variances are equal or unequal. So we could do we could do a left or right tail test. We could test whether the variance of left-handers is greater than the variance of the right-handers, or the other way around. But in this case, the alternative now is the point. It's the other part. We have the point included here on the continuum. So it's everything else. So it's that the left-handers is different to the variance of the right-handers. Okay? Our significance level, the significance level is alpha. Let's do it as 0.05, okay, the 5% level. Okay? We're not going to kill anybody here if we get the variance of the left-handers wrong, if that makes sense. The test statistic right, is, it's an F. It's equal to S1 squared over S2 squared. Now, the important thing, the way we've set up our tables is we always put the larger variance in on the top. But irrespective of that, this is a two-tailed test, because I don't mind if I show that the left-hander's variance is less than the right-hander's variance, and I don't mind if I show that the variance of the left-handers is greater than the variance of the right-handers. Either way, that'll show that they're actually different. Okay, so this is a two-tailed test. So putting in the largest variance, so we're going to say my F is now equal to, excuse me, the larger variance is the SL squared, yeah? So it's the left-hander squared divided by the right-handers squared, if that makes sense, their variances. So it's equal to 38.275 divided by 26.895, which gives us a magnitude of the difference between them. Excuse me, I have a bit of a cold. If you see, if there was no difference between the variances, SL squared and SR squared would be the same. So F would be equal to 1. But what we actually have here is that 38.275 divided by 26.895 gives us a value of, well, it gives us a value there of 1.423. So 1.423. That's the magnitude of the difference between them two variances. Yeah. Okay. Now, under the null position, where they're the same, okay, which is what we assume to be true, this should be equal to 1. If that makes sense. Yeah. So now we have our hypothesis, step 1, step 2, step 3. Now what we need to do is we need to calculate our critical values for this particular test. Yeah. So let's say step 4 is our critical values. Okay? And as I said earlier on, a test of the difference between two population variances is modeled. Its sample distribution is modeled using an F distribution. So we have to use an F distribution. So let's just draw an F distribution, which is, it depends on its degrees of freedom. Okay, but it's typically skewed. Okay? And I said it's a two-tailed test. So if there was no difference, then ratios would be 1. Okay? So we've forced the bigger one in on the top here. So we'll always know we're always going to get a value greater than 1. Okay, so we're always going to have our test statistic over in the right-hand tail. It just happens that that's where we've given you tables for right-hand tail areas. But effectively, because it's a two-tail test, okay, I have alpha over 2 goes into this tail. Okay, so I need to know the critical value here now that has alpha over 2, which is equal to 0.025 of the area in the right-hand tail, which also means then that there's an alpha over 2 over here. Okay? Okay? There's an alpha over 2 in here. So there's actually two critical values. If I put these in the other way around, I'd get a number that's less than 1, and I'd be looking in the left-hand tail. But we're forcing you to be over here. So the question is now is what's that critical value here that has 0.025 of the area to the right-hand side of it? And to figure that out, we need to go to our tables. Okay? Now, we need to take into consideration two sets of degrees of freedom. Okay, so we have degrees of freedom df1 for the left-handers is on the top, and we have degrees of freedom 2 for the right-handers on the bottom. Okay, and then degrees of freedom are how did we calculate the variances? You can see we divided by n minus 1. Okay, so we're looking now for an F distribution. Okay, an F distribution that has 0.025 of the area to the right hand side. Okay, and we've given you tables. Okay, we have tables that give you the F distribution. So here they are. Here it's actually. So I'm looking at the statistical formula and tables, postgraduate studies. I authored these with some colleagues here in NCI. And we're going to page 34 of them tables, which 34 and also 35, okay? But the small print says, this is a table of the F distribution. Their critical values for right-hand tail areas equal to 0.025. And across the top row is the degrees of freedom 1, which is the top part of the test statistic. And down the first column here is degrees of freedom 2, which is degrees of freedom associated with your second variance, your smaller variance. So in our case here, we're going to be looking at our degrees of freedom on the top is, well, the group that went in on the top were the left-handers, and the left-handers was only 11 observations. So the degrees of freedom here is equal to 11 minus 1, which is equal to 10. So we're looking at 10, okay? And then we're going to come down here, degrees of freedom 2 is for the right-handers, which is 12, which is equal to 12 minus 1, which is equal to 11. And we're going to triangulate in now, yeah? So we're looking at 10 and 11. So when I go to 10, across the first row, down, so across you see the column here that has a 10 on it, and then when I triangulate down to the row that's 11 for the second degrees of freedom, I get 3.53. Probably can't really see that there. It's not really in focus. It's 3.53. That gives me 3.53. Effectively, what we're saying is that this critical value here is 3.53 units. Yeah, that's where that's positioned, away from 1. But effectively, our test statistic is 1 point. There's our F value here. That's our F is equal to 1.423. So we're not in the rejection region. So step 5 is our decision. Our decision, okay, is clearly the F is not bigger than the critical value. What I mean by that is 1.423 is not bigger than 3.53. And as such, we fail to reject. Okay. So what does that mean? It means we haven't moved away from this particular position. So we now know that the variances, we're going to continue now. Now we're going to do the test. So Celine, we're actually into the test now, which is the test to see whether the average of those two groups, the left-handers and the right-handers, is different to each other. But what we do know now is this, is that we're going to work under the assumption that the two variances are equal to each other. Okay. So now we're into the independent samples t-test. So let us do that, because we failed to reject. If we had have rejected, we would have done an independent samples t-test assuming unequal variances. But in this case, we're assuming the variances are equal. Okay? So let me just move on here. So now we're into the test. Okay? The test of the difference between two population means, two population mean values, means. Okay? That's our independent samples t-test that we're going to undertake here. So it's an independent samples t-test assuming variances are equal. So var equal. Okay, that's what we're assuming associated with this. So now our hypothesis has a null position, has an alternative position. We want to see, is there evidence to show that they're different to each other? So is the mu of the left-handers different to the mu of the right-handers? That's all we need to really show. So the null position is we're going to assume that the left-handers are equal to the right-handers. Okay. Now, once again, we're not going to kill anybody here, so we're going to take a significance level of 5%. Significance. Don't think we're going to kill anybody. Significance level. Our alpha is equal to 0.05. And our test statistic, okay? Now, once again, we've given you tables. Our test statistic, we're going to go to the independent samples t-test, assuming equal variances. Okay? So we go back down here somewhere, which is on page, you see it's on, it's on page 16. And page 16 says it's a test statistic. It's a test statistic for a test of the difference between two population means where the sigmas are unknown, but they're assumed to be equal. Okay. So I know we don't know the sigmas, we don't know the variances, yeah. Okay. We don't know the sigma squareds, hence we don't know the sigmas, but they're unknown. But we're going to assume that they're equal from the test that we've just done. So now we have a test statistic. The test statistic is t is equal to x1 bar minus x2 bar minus mu1 minus mu2 divided by, and we're going to calculate a pooled variance because we're assuming them to be equal. So we're going to throw the two things in together to give us a better understanding of the variance. So we've got sp squared over n1 plus sp squared over n2, and it's the square root of that. That's the standard error here for the difference between two population means when the variances are assumed equal, where sp squared is equal to n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared divided by n1 plus n2 minus 2. Okay? So before we can calculate the test statistic, we need to calculate a new measure of our variance, okay, which takes into consideration the two measures that we've already got for that particular variance, if that makes sense, or for our two variances. So we've already got S1 and S2. So we know that, let's say S1, it doesn't matter who we call, which we call which, yeah. So let's say that S1 is, so our pooled variance now is sp squared is going to be equal to the sample size for the left-handers minus 1 times the variance of the left-handers, okay, plus the sample size of the right-handers minus 1 times the variance of the right-handers, divided by the sample size of the left-handers plus the sample size of the right-handers minus 2. So what we end up with is sp squared is actually equal to, well, the left-handers was size 11, so it's 11 minus 1 times its variance, and we've calculated its variance already. We know it's 38.275, so times 38.275, plus the size of the sample, the right-handers, is 12 minus 1 times its variance, and its variance was 26.895. So 26.895 was its variance. And that all needs to be divided by the first sample size, which is 11, plus the second sample size, which is 12 minus 2. And when I do that on the calculator, okay, guys, so when we do this on the calculator, I have 10, It's 10 times 38. That gives us 38275, gives us 382.75 plus, this is actually 11 times 26.895. That gives us a total of 670. Okay, and you can see that 12 minus 2 gives us 10. 10 plus the 11 gives us 21. So if I divide that by 21, that gives me a new measure of variance of 32.314. This is a better measure of our variance. Yeah, we had two different measures of variance. Yeah, we were assuming that the variances are equal, but we had two estimates of the measures. We had 26.89 and we had 38.275. This is now a better measure because it pools them all together. Right? So now the test statistic, or t value, is equal to, let's say, it's x bar of the left-handers minus x bar of the right-handers minus mu of the left-handers minus mu of the right-handers divided by SP squared over the sample size of the left-handers plus SP squared over the sample size of the right-handers. It's the square root of that. Okay? We have x bar for the left-handers and x bar for the right-handers. Actually, under the null position, which we assume to be true, we see that mu of L is equal to mu of R, which means that mu of L minus mu of R is equal to 0 under the null position, right? Under the null position, which we assume to be true. So this is actually 0. So the test statistic now becomes t is equal to the left-hander's mean, okay, which is 153, minus the right-hander's mean, which is 147, okay? Excuse me, minus mu of L minus mu of R, which is the null position. See, this test statistic is testing how far the two samples are away from each other relative to the null position that we're assuming to be true. Okay? So it's minus 0 all over SP squared, which is 32.314 over the left-hander sample size, which is 11, plus SP squared, which is 32.314 over 12, the size of the second sample, okay? And it's the square root of that. So a lot of work going on here. Okay, so let me continue. Okay, I hope everybody's still with me. I still have 6 people here. Wow, you guys are heroes, yeah, lasting this long. Yeah. Okay, so now we end up with t. Our t value is equal to, we have, it's 153 minus 147. Should know that there. That's equal to 6 divided by, I'm just going to do these in stages here. It's 32.314 divided by 11. Okay, plus, I'll put in brackets, 32.314 divided by 12. Okay, which gives me a value of 5.630. So it's the square root of 5.630. Okay, and that's going to give me a value. So when I do that now, I get 6 divided by the square root of 5.630 gives me a value of 2.5. It's 2.529 to 3 decimal places. Okay, and that's the magnitude of the difference between the two main values. Okay, but let's just keep in mind where we currently are. We've done step 1, which is defining the hypothesis. We've set our significance level at 5%. Step 3 is we've calculated the magnitude of the difference between the two samples, okay, using our test statistic, and the test statistic that was associated with assuming equal variances, okay, that the two samples were drawn from populations with equal variances, okay. And we've gone through all of that work to get this test statistic, and this test statistic is 2.529. Now what we need to do is, step 4 is we need to calculate our critical values. Okay? And what we have is, excuse me, this is the alternative is not equals to, so this is a two-tailed test. Okay? So we're going to put alpha over 2 over here, and we're going to put alpha over 2 over here, and this is positioned on 0. Okay? And we're going to get a critical value 1 and a critical value 2. Okay? How do I find them critical values? Well, we go to our t-distribution tables, and we ask the t-distribution tables what value along this axis here, okay, has alpha over 2, which is 0.025 of the area to its right-hand side. Okay? Now, our tables only give you the right-hand side situation. But because this is a symmetrical distribution, you'll just negate it to get the other critical value. So what do we end up with? So our t distribution tables, here's our formula tables, are on page 28 and page 29. And I'm interested in how much area did I put in the right-hand tail. I put 0.025 in the right-hand tail. And the degrees of freedom are, well, what did we divide our variance by? N1 plus N2. So our degrees of freedom is N1 plus N2 minus 2, which gives us, that was a value of 11 plus 12 minus 2 gave us a value of 21, if I'm not mistaken. Yeah. So I'm going to come down here to 21, and I'm going to come across to 0.025, which gives me a value of 2.080. So when I triangulate in, I get 2.080. So effectively, what we have is that this value here is 2.080. That's the value, a critical value that has 0.025 the area to the right of it, which means this value over here, this critical value here is minus 2.080. But look, our test statistic is out here. It's 2.529, which is bigger than that. So we reject, we're in the rejection region. Yeah. So now our decision, okay, our decision is clearly our t is bigger than our c. What I mean by that is 2.529 is bigger than our 2.080. And as such, okay, we reject H0 in favor of HA at the 5% level of significance, okay. And now because we've rejected, we now infer and infer, okay, that the average time for left-handed golfers, okay, to complete a round, is different, okay, to the average time taken by right-handed golfers. Okay, there you go. And we're confident about that because we've rejected. Okay, guys, here we go. So, Celine, are you still with me? Are you still there? Hopefully you're still there. I'm not going through a fair bit of paper here now for this particular test. But anyway, that's it, guys. So I think, look, to be honest with you, that was a fair bit of work to be done in this live stream. That was an hour. Yes, you're still there. Brilliant. Celine, maybe I'll just ask you a question there. Did this muddy things up a bit more, or did it sort of make things a little bit more clearer for you? Was this helpful in any way? Is there have you any other questions while you're there? Okay, a bit clearer. Well, that's good to hear. I do accept that. Look, that was a lot to go through. What I did do in this particular case, just to be exhaustive, yeah. Okay. Well, I actually did it all together, yeah. FXK, brilliant. Okay, that's great. What I did it all together was, and it doesn't say in this question to assume that the variances are equal or unequal, but I did the testing anyway, and technically you would need to do the F test before you do the independent samples T test to figure out whether variances are equal or unequal, because that determines which test statistic to go for. In this case, we chose the pooled one. But in a question, it really should say to assume whether it's equal or unequal, so that you can actually just get into your independent samples T test. Okay, guys, I think I'll leave it there if that's okay. Just coming up to an hour now, and I thank you all for joining in. And what I think I'll do is maybe we'll run another one of these sessions next week at the same time. Either on Tuesday at the same time, and only at 3:00, either on the Tuesday or the Wednesday. I'll confirm through emails during the week, if that makes sense. If you have any specific questions, maybe you can send them on to me through my email as well, which is jonathan.lambert@ncirl.ie. Okay. So guys, thanks again for joining me. Okay? And this video will be available after YouTube does the processing on it. It will be available online. Okay, brilliant, Frank. Okay, thanks, Jen. Okay, guys. Okay, talk to you soon. Okay, bye bye.